early days of rocket technology were littered with spectacular failures. Cold War adversaries, the Soviet Union and the United States, were in a rush to acquire missile technology to deliver the newly developed hydrogen bomb. During the Second World War, Germany had been working on ballistic rockets. Many of their early attempts had also been unsuccessful. By October 1942, the German team, led by Wernher von Braun, had a workable prototype. When the weapons went into mass production, V-2 attacks were launched against Britain and Belgium. With the fall of Berlin, Russia and America were keen to get their hands on V-2 technology, and German technicians captured at the end of the war were vital to the early rocket programs of both sides. In the 1950s, the Soviet Union began work with clustered engines, and the R-7, the forerunner of today's Soyuz, emerged. The new R-7 featured 2 central stages flanked by 4 boosters, a configuration that's still used today. It could deliver a heavy thermonuclear warhead to a target in North America. And the R-7 was powerful enough to put a satellite into orbit. On October 4th, 1957, the Soviet Union launched an 83-kilogram satellite called Sputnik, and everything changed. As it orbited, Sputnik transmitted a beep that could be picked up by radio as it passed overhead. America took this as a direct challenge. The US had 2 candidates close to launching a satellite: an Army team with its Jupiter-C missile, headed by German V-2 engineer Wernher von Braun, and a naval team called Vanguard. Compared to the Army's Jupiter-1, Vanguard was largely unproven. But because the US was reluctant to rely upon von Braun and his German team, Vanguard was given the task of launching America's first satellite. However, the Russians had a new surprise. 1 month before Vanguard's launch date, and barely a month after Sputnik's flight, another R-7 was on the pad. This was the launch of Sputnik 2. And this time there was a passenger, a terrier called Laika. In the US, Cold War paranoia was becoming extreme.
It gets the American people alarmed that a foreign country, especially an enemy country, can do this, and we fear this.
Pressure was building on the Vanguard team to salvage American pride. In addition to the reporters and photographers covering the event, it was announced that the launch from Cape Canaveral would be screened live. It was a national humiliation.
And here, Pickering, Van Allen, von Braun.
Von Braun's team was given the go-ahead. In weeks, the group developed a satellite named Explorer-1 that was a fraction the size of Sputnik.
Four-stage Jupiter-C.
Unlike Sputnik, which just carried a radio transmitter, Explorer-1 contained a scientific payload.
News of the day has shown you
The Juno-1 was a modified Redstone rocket with a rotating upper stage, a simple technique devised by von Braun for doing away with a final stage guidance system.
The four-stage Jupiter-C in the tense period before time zero at 10:48 p.m. The last 3 stages are set spinning on takeoff for guidance purposes.
It was simple, but it meant that Juno could not deliver its payload accurately to a circular orbit. But the Americans were in a hurry.
In 1958, free men everywhere lifted their gaze to Freedom's satellite.
Later in 1958, President Eisenhower established a civilian-led space agency which absorbed much of the Army missile unit as well as the Vanguard program. It would be known as NASA. In 1959, NASA selected 7 astronauts for a manned space program, which only existed on paper. Russia also had selected a cosmonaut corps and was working to put the first man into orbit. The research, backed by huge engineering budgets, was becoming a proxy war between the superpowers, and so far the Soviet Union was winning. But NASA had inherited the X-15 program, a rocket-powered aircraft that was delivering valuable data about flight control at the boundaries of the atmosphere. The X-15 glided back to the ground without power, and the techniques gathered here were of benefit to NASA when the space shuttle was in development. One of the X-15's pilots would join NASA in its second intake of astronauts. His name was Neil Armstrong. But the Soviets were forging ahead. After several mishaps, they had returned a pair of dogs, Belka and Strelka, safely from space. And in 1961, they were preparing to put a man in orbit. On the 12th of April 1961, a young Air Force pilot climbed into his Vostok 1 capsule. His name was Yuri Gagarin. The first man in space. The Soviet Union had set the most prestigious record yet. The United States had a spacecraft, the Mercury capsule, but they needed a heavier booster to take it to orbit. Explorer 1 had been lifted by a Redstone derivative, and early unmanned Mercury flights would also use the Redstone. Alan Shepard was due to make America's first manned spaceflight, atop a Redstone, but it would be a suborbital flight. The new, more powerful Atlas would take the first astronaut into orbit, and so far, neither launcher was performing reliably. Finally, in May 1961, after a chimpanzee had tested the Mercury-Redstone combination, Alan Shepard would become the first American to fly in space. The flight lasted 15 minutes. Shepard and his Freedom 7 capsule were picked up 480 kilometres off the coast of Florida. Later that month, America's newly elected President Kennedy committed his country to a landing on the moon.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
It was the beginning of the space race, the most concerted scientific effort in history. Since the 18th century, when William Herschel discovered Uranus, telescopes have been getting bigger. Increases in size allowed us to see more distant objects. But it was not until Edwin Hubble that we learned just how distant some of these objects were. It had been thought that our galaxy was the universe until 1924, when Hubble proved that we were just one of countless galaxies in the universe. But astronomers were reaching the technical limit of their instruments, not because of their size, but because of distortion from the Earth's atmosphere. In 1946, astronomer Lyman Spitzer proposed an orbiting telescope above the distorting veil of the atmosphere. It was a wild idea, years ahead of humanity's technical capability, but it was built, and the space telescope named after Edwin Hubble has been in orbit since 1990. No single instrument has contributed more to our understanding of the universe than the Hubble Space Telescope. But it hasn't been straightforward. Something as complex as an autonomous telescope located in the harsh environment of space needs regular maintenance, and it was only possible because of the Space Shuttle and its ability to serve as a work platform. Without the Space Shuttle and its regular servicing missions, Hubble's initial design inadequacy and a series of component failures would have left it as a very expensive piece of space junk. After Discovery's deployment of the Space Telescope in 1990, there were 4 subsequent servicing flights. Hubble was both repaired and upgraded on these missions.
As the vehicle passes through the area of maximum dynamic pressure.
Atlantis, Houston, no action.
With the shuttle now withdrawn from service, there will be no more on-orbit maintenance. Components readied for Hubble's last servicing mission included new gyros, batteries, fine guidance sensor, astronaut tools, support hardware, a new docking ring, the carrier systems, and 2 new instruments. But building the hardware and packing it for flight to orbit was just a part of the preparation. At NASA's Neutral Buoyancy Laboratory in Houston, mock-ups of the shuttle's payload bay and the Hubble were available for the exhaustive training the astronauts needed. Conditions have to match those that the astronauts will experience on orbit. Problems encountered in the pool are solved before the team flies. In 2004, when a power supply blew, Hubble lost its imaging spectrograph. Repairing this component was something never envisaged by the telescope's designers, so special techniques and tools had to be developed. As the flight date approached, all the hardware was packed into special shipping containers for transfer to the launch site, where the next phase of the operation began. On March 2nd, 2004, an Ariane 5 blasted off from Kourou in French Guiana. It carried the Rosetta probe, one of the most ambitious deep space missions yet launched. Recently, it was brought out of a 3-year hibernation.
When I first heard the idea of Rosetta, I thought it would be extremely difficult.
We've never flown a spacecraft to a comet.
Its mission is to rendezvous with a comet, and it has had to travel a complex flight path to get there. Previous deep space probes have carried radioisotope power supplies, but Rosetta is designed with solar panels. It also carries a lander called Philae. The course Rosetta has followed has taken it past Mars and then back past Earth to gain assistance from the planet's gravitational fields. The probe skimmed past Mars at just 250 kilometres. Originally intended to meet Comet Virtanen, launch delays meant a new comet had to be targeted. Rosetta reached a maximum distance from the Sun of 780 million kilometres, taking it beyond the orbit of Jupiter. During its cruise, Rosetta photographed asteroids, Steins and Lutetia. Starting last May, a series of thruster burns were monitored by members of the Rosetta mission team. The first of 3 major burns took place, with Rosetta 500 million kilometres away. It used 218 kilograms of fuel and lasted 7 hours and 16 minutes. It brought Rosetta into phase with its target, Comet Churyumov-Gerasimenko. Over several months, 10 separate corrections were needed, and by August, the probe was roughly 100 kilometres from the comet. Soon, team members began seeing just what Comet 67P Churyumov-Gerasimenko looked like. These pictures are a computer-generated recreation based on the first images of the comet. As it's still a long way from the Sun, no tail has yet developed.
It's only when you come closer to the Sun, this comet
activity, this material starts to become active and it's outgassing, and then the cometary tail is formed, and this is what we normally see in the sky.
Because the comet's mass is so small, Rosetta will have to be at a very low relative speed to orbit it. At the moment, the probe is carrying out a series of triangular manoeuvres to track with the comet. Black and white images relayed by Rosetta's navigation cameras surprised scientists who were expecting a much smoother object where traces of surface ice were apparent. Of 5 possible landing areas, landing site J was selected. For the Philae lander, it had the best combination of solar illumination and radio access to the Rosetta mothership.
The shape of the comet is definitely a bit unexpected. I consider it at the same time fantastic. It's a unique object. On the other side, has posed us some headaches in finding proper landing site because of this unusual shape.
The Philae lander was released from a distance of 20 kilometres. Its 4-hour drop was timed so that it would arrive at the intended area, taking into account the comet's 12-hour rotational period. Philae's 3 legs are tipped with small screws designed to anchor the craft on contact with the surface. On Earth, the lander weighs 100 kilograms, but although Comet 67P is the size of a mountain, its gravity is very slight. At the comet's surface, Philae has a weight equivalent to a piece of paper. This is a problem that leg screws and a small anchoring harpoon were designed to overcome. In addition, a small thruster at the top of the lander would push the craft down on contact with the surface. This is how it was supposed to happen, but scientists who had to wait for a message relayed via Rosetta were confused. It took an hour for a confirmation signal to reach mission control in Darmstadt, and initially there was celebration. But after hours of analysis, it became apparent that the anchoring devices had all failed, and the probe had bounced back up to a height of 1 kilometre. After initial contact within 1 metre of the intended landing ellipse, Philae finally came to rest at the base of a cliff. It was functioning well and sent back images of its surrounds, including this picture of its foot wedged up against the cliff. This was not a good place, as the craft's solar panels will receive only limited sunlight. While its batteries still had enough charge, the lander was asked to drill out a surface sample, analyse it and relay the results to the Rosetta mothercraft. This went smoothly, but Philae's batteries are now flat. It is hoped that as the comet approaches the Sun, the craft will receive enough light to recharge its power supply. Meanwhile, the Rosetta probe will continue to follow Comet 67P as it warms and develops its characteristic tail. Since the earliest days of rocket launches, thousands of satellites have been delivered to Earth orbit. Today, an awareness of orbital debris means satellites at the end of their lives are set on a course that will see them burn up in the atmosphere. But many satellites remain aloft, and upper stages containing unburnt fuel will continue to drift, sometimes with alarming consequences. A cloud of orbital debris has been building up around our planet. This has serious implications for new satellite launches. ESA tracks the larger pieces of this orbital debris to see whether current satellites are in danger of collision. Ground stations are important in determining the orbital parameters of defunct satellites that can no longer communicate. only 7% of monitored objects are functioning satellites.
Of the 16,000 to 17,000 objects that we can track from ground stations up there, just about 1,000 are operational spacecraft. All the rest are remnants of past spaceflight activities, and more than one-half of these objects are in fact fragments from on-orbit collisions recently, and also fragments from on-orbit explosions.
Satellites at the greatest risk are those in north-south orbits, like the Earth observation satellites. The tracks of these craft converge at the poles, and this is where the highest likelihood of collision exists. There have already been 4 major collisions in low Earth orbit. The most serious impact was the one between an Iridium satellite and a defunct Cosmos satellite in February 2009. They collided at a relative speed of around 42,000 kilometers per hour, creating an additional 2,000 pieces of debris. This debris cloud has continued to spread across different polar orbits. According to international space law, responsibility for any debris or abandoned satellite remains with the owner. Regulations require new satellites to carry enough fuel to enter a decaying orbit at the end of their usable life. Schemes to deorbit dangerous objects are being devised, but they are very expensive. In the 1950s, when the USSR and the USA emerged as post-war superpowers, ballistic missile technology was pushed centre stage. Early results were frequently catastrophic. Because America could station missiles in Western Europe, they developed short-range weapons. But the Soviet Union had to develop the capability of delivering a heavy nuclear payload from Russia to the United States. The R-7 Semyorka was the world's first intercontinental ballistic missile. It also gave the USSR the ability to launch a satellite into orbit, a huge advantage in the early years of spaceflight. Americans were alarmed when their communist enemy began setting space records that were years beyond their free market technology. In 1958, President Eisenhower established NASA to consolidate America's space effort in one civilian agency, and the newly assembled team started work in a hurry. The overwhelming feeling in the US was they were well behind the Russians. NASA absorbed the US Air Force's Man in Space Soonest program. It was renamed Project Mercury. Engineers began work on a titanium space capsule that could sustain a human in the vacuum of space and withstand the searing heat of re-entry. As prospective astronauts, 110 military test pilots met NASA's basic prerequisites and were invited to enter the rigorous selection process devised to choose the Project Mercury team. As well as being a qualified jet pilot with 1,500 flying hours, applicants had to have an engineering background and be younger than 40 at the time of selection. But some pilots were reluctant to volunteer, feeling that astronauts would do little flying, simply serving as glamorized lab rats. When the first 7 astronauts were introduced at a press conference, they were lauded as movie stars. It was 1959, and the only living thing to have orbited the Earth was a Russian dog. It was known that the Soviet Union was working to get a man into space, but NASA was determined that an American would get there first, so they began modifying the proven Redstone booster. Although it did not have the power to launch a man into orbit, they planned to make a series of short suborbital flights to test their technology. NASA's first manned orbital flights would use the SM-65 Atlas missile, a much larger ICBM that was being modified to carry the Mercury capsule. But reliability was a problem. In September 1959, during the static test of an Atlas, a turbopump failure triggered a complete shutdown. But fire persisted. The damaged pump was leaking oxygen. Damage to the pad took 7 months to repair. Because so many boosters were blowing up, an emergency escape system was developed. A tower atop the capsule housed a small but powerful solid fuel rocket that could pull the spacecraft clear of a catastrophic failure. To test the escape system, a new booster known as Little Joe was built. It was based on existing technology and cheaper than using a full-scale rocket. The escape tower was tested on the ground at maximum dynamic stress and at very high altitude. A complex sequence of events had to happen automatically to return the capsule safely to an ocean splashdown. This would give problems at a later stage of testing. The capsule itself had to be tested, and the new astronauts were each given an area of specialisation. Engineers would get direct input from the people who would fly the Mercury spacecraft. At NASA's Langley Research Center, the new astronauts were schooled in concepts such as retrofire and re-entry. The Mercury 7 all had engineering degrees, and even at this stage, their feedback was leading to redesign of capsule control systems. Simulators were developed that gave an astronaut the sensation of a tumbling capsule, allowing the team to gain experience before they flew. On special flights, they had a taste of zero gravity. Towards the end of 1960, the Mercury team was nearing full-scale flight tests. The first Mercury-Redstone combination would make an unmanned suborbital flight to qualify the system. Alan Shepard had been selected to make the first manned flight, and it seemed he would be the first man in space. Known as MR1, this first Project Mercury vehicle was assembled at Cape Canaveral's Launch Complex 5. It would test the automated flight control, the launch and tracking system, as well as recovery procedures. The capsule's automated abort system, a vital safety feature, would also be tested. It would be known as the 4-inch flight. The booster engines abruptly stopped, and the escape tower was jettisoned as programmed at the end of the boost phase. This triggered the deployment of the parachutes, leaving the capsule in place atop the fully fueled Redstone. The problem had been caused when power plugs at the base of the Redstone disengaged in the wrong sequence. A technician had filed down a contact to make it fit. A new booster was flown in to replace the damaged one. The same capsule would be used for the second attempt, but it had to be refurbished. The electrical connections that had triggered the engine shutdown were redesigned, and the automated sequencing for jettisoning the escape tower had been rethought. Main engine cutoff could only trigger the release of the tower 137 seconds after liftoff. The delayed flight, now known as MR1A, was launched on December the 19th. It flew higher than expected, but was otherwise flawless. Yet NASA had lost a month in their rush to put a man in space first. A chimp would make the next flight. Engineers were uncertain about risking an astronaut when the booster was still flying too high. Chimp number 65, known as Ham, would fly before a human, and the astronauts were not happy. The flight was designated MR2, and if it all went well, Alan Shepard would be next. But things did not go well. An overactive pump depleted the engine's liquid oxygen too quickly, and when the engine pressure dropped, the escape system kicked in, lifting Ham's capsule to an altitude of 253 kilometres, far higher than had been planned. Because the escape system had activated, the capsule's retro rockets had been jettisoned, meaning the spacecraft's ballistic return to Earth could not be slowed. Ham, the Astro chimp, experienced more than 14 G during re-entry. Next, a valve opened early and the capsule lost pressure. Finally, when the capsule splashed down, 200 kilometres beyond the planned point, the impact bag was shredded and the heat shield had punched holes in the capsule base, flooding it with seawater. Ham had survived, protected inside the small compartment which functioned as his spacesuit, but debate about whether the system was ready to take an astronaut began. An extra flight to sort out the bugs in the Redstone booster was scheduled. At the same time, NASA was preparing the much larger Atlas booster in readiness for orbital flights. Developed as a weapons delivery missile, the Atlas was also being used to launch satellites. Its very thin stainless steel skin made it very light, but it was also fragile, and its early safety record was not good. At its first launch, carrying a dummy Mercury capsule, the Atlas's thin skin buckled. It would be strengthened for all subsequent flights. It had not been publicly announced that Alan Shepard would make the first Mercury flight, but team members were growing in confidence that he would become the first man in space. But his flight was postponed several times. A replacement for the booster needed for the extra development test was slow in coming. An original launch in February 1961 was put off till March, then to May. In April, the Soviet team had yet another surprise. After a heartfelt farewell, Colonel Yuri Gagarin prepared to enter his Vostok spacecraft. The flight and Gagarin's identity had been a closely guarded secret, with none of his cosmonaut colleagues being aware who was to make the first attempt. The craft would function automatically, with Yuri Gagarin needing to enter a code to unlock the controls should it be necessary. Gagarin completed one full orbit of the Earth and returned safely. He was only in radio contact while flying over Russia. The first cosmonaut was a hero. The first manned spaceflight captured the world's attention, and it surprised the Soviet Union as much as anyone. The smiling Gagarin became a huge asset to his country. The Soviet leaders wanted more, and government funding for space was assured. One group not happy about Gagarin's flight were the Mercury astronauts. While they were getting plenty of publicity, all they had done so far was train. Alan Shepard had missed the opportunity to be first, and his short suborbital flight would be an anticlimax after the Soviet triumph. In the early hours of May the 5th, 1961, Shepard arrived at Cape Canaveral's Launch Complex 5. A Redstone launcher stood waiting, topped with a Mercury capsule Shepard had named Freedom 7. It was a pointed dig at the Soviet Union's political system. American media had branded Gagarin's flight as a propaganda stunt rather than a scientific achievement.
3, 2, 1, 0. Liftoff. All right, liftoff, and the clock has started. Yes, sir. Reading you loud and clear.
After a delay, Freedom 7 blasted off. The flight climbed to a height of 187 kilometers.
PSI, oxygen is go. What a beautiful view.
At several points, Shepard took manual control of his craft, but it was over quickly, with the flight lasting just 15 minutes and 22 seconds. Freedom 7 splashed down in the Atlantic off the coast of Florida. Though Shepard had not orbited, Project Mercury had put a man in space, and America was keen to catch up. The idea that there was a race between the superpowers was becoming all too clear. Launched in June 2003, ESA's Mars Express reached Mars in less than 7 months. It took advantage of the planet's closest pass by Earth in 60,000 years. It was the European Space Agency's first mission to the Red Planet, and it rose from the ashes of Russia's failed Mars 96 mission. Europe had made a major technical contribution to the Russian probe, but after a successful launch, the 4th stage failed to reignite, and Mars 96 burned up in the Earth's atmosphere. Though there is no outward similarity between the probes, Mars Express contains many of the same sensors and instrumentation as its Russian predecessor. Since its arrival at Mars, the probe has been imaging the Martian surface. Its instruments are designed to find out more about the planet's atmosphere and its geology, including evidence of surface water that may have existed in the past. Contour images of the surface reveal features that are familiar to us as having been caused by volcanic eruption, but all tectonic activity has ceased long ago. Mars shows signs of erosion too, yet the channels have long since dried. But the fact that water once flowed here may mean that rudimentary life got started. Just like Earth, Mars revolves on a tilted axis, giving it seasons, but because the planet's orbit is highly elliptical, there is broad variability in surface temperatures. In summer it can reach 20 degrees Celsius, dropping to -90 overnight. Mars also has polar ice caps, but they're made of water ice covered in winter by a layer of frozen CO2. This layering process is not fully understood. Instruments on Mars Express suggest that the thin atmosphere is 95% CO2 with traces of nitrogen, oxygen and water vapour. It supports fine cloud and strong winds. Now, the only forces able to affect the surface topography are dust storms and meteor impacts. Mars Express is in an elliptical orbit around Mars at right angles to the orbit of Phobos, Mars's major moon. Recently, it made its closest approach to the tiny moon, which is too small to have a spherical shape. Phobos has the appearance of a captured asteroid, but scientists are puzzled by it. Its mass and density are lower than expected, so it's thought to be porous. Since it has been in orbit, the infrared spectrometer on Mars Express has continued to discover water, which has planetary researchers upgrading their expectations that some form of life may once have existed on Mars. Mars Express has had several mission extensions. New measures have been instituted to conserve the spacecraft's dwindling fuel reserves, and it looks like the mission will continue until its fuel finally runs out. Russia's iconic Soyuz Launcher at the Baikonur Cosmodrome. Currently, it's the only means of taking cosmonauts to the International Space Station. What makes it special is its direct lineage to the historic designs that launched the first satellite and the first man in space. The most striking outward similarity is the 4 strap-on boosters. Together these make up the first stage. The central core around which they cluster is known as the second stage, even though it ignites before launch along with the strap-ons. These stages are fueled by kerosene with a liquid oxygen oxidizer. After 118 seconds, the 4 first-stage boosters are jettisoned, and the second stage will continue burning for another 3 minutes. Like other Russian rockets, the Soyuz takes its name from one of its most frequently lifted payloads, the Soyuz spacecraft, which has been in service since 1967. Since the retirement of the US Space Shuttle, the Soyuz spacecraft has played an indispensable role in ferrying crews to and from the International Space Station. With a capacity of 3 cosmonauts, and with the ISS having a working team of 6, there need to be 2 Soyuz spacecraft on hand at the space station in case an evacuation is required. The Soyuz launch system uses very simple production techniques. Unlike the American shuttle and the Saturn V's, the Soyuz is assembled horizontally, which saves a huge amount of extra manufacturing hardware and complexity. Final integration happens on a rail car and incorporates the lifting arm that will raise the rocket at the launch pad. The trip to the pad happens at a walking pace, and it is a Russian tradition that cosmonauts due to fly will witness the rollout. At the pad, hydraulics are used to raise the Soyuz to vertical, where it is suspended above the flame pit and supported by 4 counterweighted arms. Fueling and service gantries also surround the rocket. The gantries will be withdrawn before launch, leaving the unique tulip-shaped configuration. This was originally devised to add extra support to the waiting rocket, as the Baikonur launch site is known for its strong winds. In 2011, a Soyuz launcher was being prepared for launch from a new site. It has been adapted for use at the European spaceport in French Guiana.
5, 4, 3, 2, 1, top.
With improved lift capacity and an enviable launch record, commercial satellite clients just love the Soyuz.